Let's say you're a spy. You need to receive intel from your fellow agent, but you can only communicate through a line that you know is being tapped. What message should you send to your partner so that the enemy can't understand the information being passed on to you over the line? I encourage you to pause the video and try to work out this problem yourself. At first, this seems impossible because the enemy will always know what you told your partner. Any instruction you give your agent can be copied and used by the enemy. For example, if you tell your partner to encrypt messages using a Caesar cipher, you have to reveal the shift number. This means the enemy can easily decrypt the message by performing a shift in the opposite direction. Clearly, the Caesar cipher is too easy to reverse engineer. This issue arises due to the symmetry of the algorithm. In symmetric encryption, we encrypt and decrypt a message using the same key, making it impossible to securely send a message when other people also know the key. It would be nice if we could use a different key for encrypting and decrypting. This is what we call asymmetric encryption. Asymmetric encryption is like giving a padlock to the sender for locking their box. The padlock can be used to lock the box, but only you have the key to unlock it. Even if the padlock falls into the wrong hands, it's useless because it would be too hard to forge a key for it. This brings us to the famous RSA algorithm, which executes this idea through clever mathematics. In this video, I will give you my best explanation on how RSA works and show you how to implement it yourself. The way RSA works is the receiver generates a public key and a private key. Each key contains two integers, one of which is common. The public key is used for encryption, while the private key is kept secret and used for decryption. The sender has to convert their message to an integer, m, before their message can be encrypted. M is encrypted by raising it to the encryption exponent in the public key, and then dividing it by the common modulus. The remainder of this division is the encrypted message. Upon acquiring the encrypted message, the receiver can decrypt it through the same process. The only difference is that the number is raised to the power of the decryption exponent in the private key. Now you may be wondering how I got the numbers 5, 11, and 14. The process I'm going to show you is a heavily simplified version of industry RSA, which uses much bigger numbers to make it harder to crack. However, the idea is the same. First, we begin by picking two distinct prime numbers, p and q. For this example, we will choose 2 and 7. The common modulus n is the product of p and q, giving us 14. Next, we need to calculate Euler's totient function of the common modulus. We can do this by listing out all the numbers less than 14 and counting the ones that don't share a factor with p or q. This is tedious, but thankfully we can use this formula instead. The proof for this formula is left as an exercise for the viewer. Once we have phi, we can choose our encryption exponent, which has to be coprime with phi and n. A quick way to do this is to just subtract 1 from phi, because it's guaranteed to not share any factors with phi or n. For our decryption exponent, we want to pick a number that obeys the following rule. It turns out phi plus e will always satisfy this requirement if e equals phi minus 1. We have finally devised a method for implementing our own RSA. This is obviously not the most secure encryption because 14 is small enough for us to guess its prime factors. If we use the large prime factors and a less obvious method to generate our exponents, it would take much longer to break the encryption, at least for classical computers. Coming back to the riddle, a simple RSA would suffice, assuming the enemy wasn't a group of expert mathematicians.